Uh, Good afternoon, everyone. And so this is our second lecture on the canonical distribution. And let me remind you where we stopped last time. We derived a canonical distribution of probabilities. And from that, I calculated, introduced the partition function and explained it to you how it's related to the free energy of the system. Once we know the free energy of the system, we can calculate all macroscopic quantities like entropy, pressure, chemical potential, and basically to derive all thermodynamic uh, information about the system. Uh, Having this distribution of probabilities, a canonical distribution, we can, in principle, calculate average of any quantity in this distribution. And this is what we did for the internal energy when we calculated the internal energy in the canonical uh, distribution and how we derived the expression for the free energy. But now we have a question. How wide is this distribution? Because remember that this is the example which we considered at the end of the last lecture. So in principle, because we have a probability distribution for different energies at constant temperatures, so energies, the energy can fluctuate about the mean energy U determined by the temperature. And the mean energy we calculated before as being the minus d over d beta of the logarithm of the partition function using the differentiation trick. This is basically a definition of the mean energy as being the mean average of the Hamiltonian, which gives the energy of the system, averaged with probabilities, then integrating of the whole phase space and normalizing by partition function. Okay. Now we want to calculate fluctuations. Basically, we want to understand how probable is the mean energy. So basically, how large are fluctuations about the average value of the energy. And to do that, we use again the differentiation trick. We differentiate now the average energy with respect to beta once more. And what we get, this is a fraction. And to differentiate it over beta, we need to differentiate the numerator and denominator. When we differentiate the numerator, we get, when we differentiate with respect to beta, we get an extra h here in the numerator, and as a result, we get this term, because differentiating over beta gives us minus h, and so it becomes minus h squared. Well, then we need to differentiate the denominator. When we differentiate the denominator, we get the denominator squared. But then we need to differentiate this with respect to beta, and this is how we get exactly the same integral in the numerator. So differentiating this guy with respect to beta, we get it in the denominator squared times its derivative, and this is the this integral squared. So you can immediately recognize that this first term is nothing else as h squared averaged, and this guy is just this guy squared. So this is the average energy or average value of the Hamiltonian of the system. So the derivative of the internal energy with respect to beta give us the variance of the energy. Okay. So this is the main formula. We actually used the same differentiation trick to derive fluctuations in the microcanonical ensemble. Now we remember that we know if we differentiate the average energy with respect to beta, the left-hand side, we can change that derivative with respect to the derivative with respect to temperature using a change of variables. This is a chain rule. And so we can rewrite it as the derivative of the internal energy with respect to temperature, which gives us the heat capacity of the system. Okay, so from here we see that the variance of the average energy in the system is proportional to the heat capacity. Now, when the system has n particle, obviously the energy of the system is proportional to the number of the particles. So squared energy is proportional to n squared for macroscopic systems. But the heat capacity of the system is proportional to the number of particles. So if we divide both parts by n squared, then here we get the variance per particle of the of the internal energy, and here we will get an extra factor 1 over n. Okay, so when n goes to infinity, fluctuations, the variance goes to 0, and fluctuations about the average energy, they are suppressed by the factor 1 over n. So they become negligible when n goes to infinity. So this is the reason why the results of the canonical and microcanonical ensembles coincide in the thermodynamic limit. Because remember that in the microcanonical ensemble, the energy of the system is fixed. Okay? In the canonical ensemble, it may fluctuate, but when the system goes to the size of the system goes to infinity, these fluctuations are suppressed by the factor 1 over n. So basically, in the thermodynamic limit, it corresponds that the energy in the thermodynamic limit becomes a constant equal to the average energy, and this is why results of these two ensembles in the thermodynamic limit will coincide. Okay, the next question we want to answer: how about that minimization principle of the free energy for the system with a fixed volume and number of particles, and which is in the thermodynamic equilibrium with the heat reservoir of the temperature T. Okay, we want to derive this minimization principle of the energy from the statistical point of view. And how we do it? So let me remind you the definition of the partition function of the canonical ensemble. It's the integral over the whole phase space, basically the sum over all states of the system, of Boltzmann factors, exponential of beta minus hp. To deal with this integral, we'll replace this factor with the following identity. We introduce a formal variable E, which stands for the energy, and integrate over all values of E, put exponential of minus beta E here, and insert a delta function, h of pq minus E. I hope that you know already from quantum mechanics what delta function is. So if you don't, basically when the delta function, the integral over E is integrated with any, you integrate the quantity, it's with delta function of, say this is variable x minus E, then what the delta function does, it just removes the integral and substitute instead of this value E, this quantity h, and this is what we get. Okay, so this is a formal substitution. So using this, let's substitute this exponent by this integral. Okay, when we do that, we get a double integral. Integral over dEs and integral over the phase volume. Now I swap these two integrals, dE and the integral over the phase volume. And because now my Boltzmann factor does not depend on the point in the phase space. It has a formal variable. I can take it out of the integral and write it down as the integral over d exponential minus beta e. And what remains here, integral over the phase volume of the system. And from here, we have this delta function. Okay. And this factor, we already met before, and maybe you can recognize it. Let me remind you, when we calculated so again, this formula, the partition function equal to this formal integral, and this integral over the phase space. Let me remind you that when we calculated the total volume of the phase space, we introduced a spherical shell in the phase space of the thickness delta, and where delta is basically the error of measurements of our energy, and then we calculated the volume inside of this spherical shell when the energy was sitting between the values or E and E plus delta, or we said that the Hamiltonian between E and E plus delta. If you look at this integral, it's basically, if we cross out this delta function and put here that h between the value of E and E plus delta, it will be exactly the phase volume of our system. But now in this integral, we substitute the instant value for the Hamiltonian to be E, okay? Because that's a delta function. Now we assume that during this interval from E plus delta, it basically corresponds to the same phase state of the system. So basically, it's our error of measurement. That's how the accuracy of how we can determine a particular state. So basically, we assume that Hamiltonian delta is small enough that the Hamiltonian does not change. So it means that this phase volume is equal to the size of this, equal to the thickness of the shell times the area of this spherical shell. And it's easy to understand that this area is exactly equal to this integral, or we can call it as the density of states at energy E. So our phase volume, which is the volume of this spherical shell, is equal to this integral times delta, okay? Which is the same as the integral taken when the Hamiltonian was sitting between E and E plus delta. Because if we assume that Hamiltonian doesn't change much between the values E and E plus delta, then the phase volume is just equal the size of the spherical shell times delta. And the area of the spherical shell is obviously exactly this, when we just assign to the Hamiltonian to be exactly the value E between E and E plus delta, okay? So, but once we know the total volume, phase volume, we know that the entropy of our system is K log of gamma, okay? And now, using this relation, we first express omega density of states, or this integral, as gamma over delta, and then we substitute for gamma this expression in terms of the entropy. And taking the exponent of this relation, we find that the gamma is equal exponential of S over KB, okay? And we can rewrite it using the inverse, the notation for the inverse temperature. We can write as 1 over delta exponential beta T times the entropy. So this is the density of states, which is equal to this integral. And we related it to the entropy of the system. Now we plug, and the entropy for calculated of the system calculated at some energy E, okay? Now we take this density and plug it in here. And this is what we get. The partition function is equal to 1 over delta. Delta is some thickness of the shell, is an irrelevant constant, which is a constant. We can basically drop it out. This is just a constant. Integral over the energy, exponential of minus beta E, and there is a second term coming from here, minus T. Okay, so we express the partition function as a one-dimensional integral over all possible energies of the system as exponential of minus beta E minus T, the entropy of the system calculated when the total energy is equal to E. Okay, so this is the formula. But now let's remind that E minus T S of E, it's exactly the free energy of the system with the total energy E. So we get a universal formula. The partition function in the canonical ensemble can be expressed as the integral over all positive energies, exponential of minus beta Helmholtz free energy calculated at the energy E, and integrating over all possible values. So this is the exact result, okay, for any system with a finite number of components. Now we want to show that in the thermodynamic limit, the dominant contribution to this integral will come from the values of E when f of E reaches its minimum. And the method we use is normally called a saddle point method, evaluations of integrals. When we basically replace, when we know that the function, the integrand has some minimum near some value, and we replace the function by its Taylor series near that minimum, and approximate this integral by that Taylor series and keep several first terms and calculate this integral. Okay, let me explain how it's done. Let's expand the free energy of the system near its minimum. We don't know yet that it's the minimum, but we'll see it in a moment. It can be a maximum. At the moment, it's just some extremal value of the functional where the first derivative is equal to 0. Let's check that the first derivative of the free energy with respect to of the Helmholtz free energy is indeed 0. So if we differentiate the free energy with respect to the Helmholtz free energy with respect to the energy, what we get from this formula, differentiating this guy with respect to the energy of the system, we get 1 minus temperature, differentiating it with respect to the energy and substituting the value equal to the average value of the system. But let me remind you now the thermodynamic equation, which says that if we take the entropy of the system and differentiate it with respect to the energy and substitute the average energy of the system, we get the inverse temperature. So if we substitute this in here, we get 1 minus T over 1 over T equal to 0. So indeed, near its average energy, the first derivative of the function of the Helmholtz free energy is equal to 0. Okay. To check that that's the minimum of this function, we need to calculate the second derivative. Okay, and check that the second derivative is positive. If the second derivative is positive, then it indeed implies that the average energy is a minimum of the free energy with respect to the of the Helmholtz free energy F with respect to the energy of the system. For that, we calculate the second derivative with respect to E, and taking into account the previous formula, it becomes minus T second derivative of the entropy with respect to the energy. Making a change of variables, now we in easy calculation, we can transform it to the following expression as 1 over t squared dt over dE, and dE over dt, it becomes the heat capacity at constant volume. So at the end, we get the following expression, 1 over T CV. And the constant, this second derivative is positive. So it implies that it's indeed, once we expand the free energy near of the Helmholtz free energy in teleseries uh, near the average value of the energy, then we get no, there is no linear term, and there is a quadratic term with a positive coefficient. So indeed, this point is the minimum of the free energy. Of course, there will be higher terms, but one can show that these higher terms will be suppressed when n goes to infinity. Even this term will discard at the end. So let's assume that all those higher terms in this Taylor series expansion, they don't contribute in the thermodynamic limit. This is how it's done in the saddle point method. We keep only the minimum value and the first quadratic contribution, okay? And we discard all higher terms. So in this approximation, this is just a constant, which becomes, we take out of the integral, which becomes this average exponential of minus beta for energy calculated at the average value of the energy, and then the integral over all values of the energy of this exponential, which is nothing else as a Gaussian integral, which is quite easy to calculate. And as I said, we discard all other terms here. So in the thermodynamic limit of the system, the heat capacity becomes infinite, and the integral has a very sharp peak near the average energy of the system. We can neglect higher order terms and obtain, so in here we have this constant contribution plus this integral, which is the Gaussian integral, which we can calculate, and here is the result, okay, for the calculation of this. If we now take the logarithm of both parts, so logarithm of the partition function is equal to the free energy calculated at the average energy of the system. This is minus beta, and plus 1/2 of log of this expression. Now, this term is of the order n. Free energy of the system is proportional to the size of the system in the thermodynamic limit. Heat capacity is also proportional to the size of the system, but there is an extra log here, okay? So this term of the order log of n, and this term of the order n. So when n goes to infinity, this term can be discarded. And what we get, we see that in the thermodynamic limit, the only contribution which survives is the minimum value of this free energy calculated in the average energy. Roughly speaking, the integral in the previous slide, it behaves like that. It's very sharply peaked near the average energy, okay? And the width of this peak is proportional to kT squared over CV, where CV is proportional to n. So there is square root of n in the denominator. And when n goes to infinity, this the width of this peak gets to 0, and the partition function in the thermodynamic limit becomes the exponential of minus beta, the minimum of the free energy, okay, where the minimum is reached at the at some average energy. So basically, this justifies that in thermodynamic limit, the free energy reaches its minimum, and correspondingly the partition function reaches its maximum. Okay. Now, once we know a behavior of the canonical ensemble in the thermodynamic limit, let's apply it to some system of interest, in particular classical ideal gas. Let's rederive all equations of states and the entropy of ideal gas using this canonical approach. First of all, let's notice that if the system consists of n non-interacting parts, in principle identical parts, they can be distinguishable like atoms in a solid, but they are we assume later on that they are identical. So if it has n non-interacting parts, the whole Hamiltonian of the system can be written as the sum of individual Hamiltonians. Okay, because there is no interaction between different parts. So then the partition function of the system becomes the integral over the phase space exponential of minus beta h1 minus beta h2 and etc. Exponential of the sum is equal to the product of exponents. And so this whole integral splits into the products of the phase integrals associated with individual parts, which are partition functions of individual parts, z1, z2, and zn. And I put here approximate because there may be an extra factor here which depends whether particles are distinguishable or not. In the case of indistinguishable particles, like in the classical ideal gas, we know that this tau contains n factorial multiplier. Okay, so we need to take that into account and divide by n factorial. In the case of the distinguishable particle, like atoms in a 1 or 2 or 3-dimensional lattice, all particles are distinguishable and there is no n factorial here. So we shouldn't divide this product of individual partition functions by n factorial. Okay. So now let's apply it to the classical ideal gas. The Hamiltonian is simple. It just has a structure. It has it's just a sum of individual kinetic energies for n non-interacting atoms, and each kinetic energy, P1 squared, P2 squared, is made of 3 terms, Px squared plus Py squared plus Pz squared. So our partition function, because all particles are indistinguishable, there is n factorial in the denominator in this case. There is the integral over the whole phase volume. There is the volume of elementary cell in the 3n dimensional, in the 6n dimensional phase space. And then that's our Boltzmann factor, exponential of minus beta energy. Now, this Boltzmann factor does not depend on coordinates. So integral over coordinates becomes trivial. And it's just nothing else as the volume of the system to the power n, because the integral over d3q for for each individual particle, it becomes just volume, and because there is n particles, so this integral, it becomes the nth power of this integral, so volume to the power n. This n factorial goes here, but the integral over each over the momentum space of each individual particles splits into n integrals, But now each integral for individual particle, it has three parts, px squared, py squared, pz squared, which do not interact. So the integral for each individual particle, it splits into three integrals. And there are n of them. So as a result, we get the integral over individual components like dpx, dpy, dpz. It gives us a q, three individual integrals over the of the momentum space of individual particles is like dpx, dpy, dpz, px squared plus py squared plus pz squared. And that gives us the integral over dp of one component, and there are three of them, so a cube of this integral. Now there is n particles, so this integral, we need to raise it to the power 3n, okay? And this integral is a simple Gaussian integral, which is easy to calculate, and this is the result. This is the result. So this is the result for the partition function of n non-interacting atoms, okay? Which we can rewrite in the form 1 over n factorial. And if we introduce for this integral, we denote this integral as a result 1 over lambda, where lambda is what's called a thermal wavelength. Then the result of that becomes v over to the power v over lambda cubed to the power n. And let me remind you that the thermal wavelength, it characterizes basically, it's a separate, characterizes two regimes of the system, classical and quantum. So when the volume for each particle is much larger than v much larger than lambda cube, we are in a completely classical regime. When the volume associated with the particle it becomes of the order lambda, we get, or even less than lambda, we get, we go to the quantum regime, and all this classical consideration, they no longer apply, because quantum partition functions of individual particles, they start overlapping. So basically this formula applies only when the volume is much larger than lambda. So we assume that lambda is sufficiently small number, which is a thermal wavelength. Okay. So once we know the partition function, then it's easy. We immediately can calculate the Helmholtz free energy of the system. And here's the result. As we see, it's indeed proportional to the number of particles and depend on the temperature and the thermal wavelength, which depends on the temperature as well. And it also depends on the concentration of particles, where concentration is the number of particles over the volume of the system. And here I already use the Stirling approximation for n factorial, okay, as we've done many times before. So if we now can calculate the chemical potential of the system, differentiating V with respect to number of the particles, and this is the immediate result. And we can also calculate the formula for the entropy, differentiating dV over dF over dt, and this is the result, which is nothing else as the Sackur-Tetrode equation, which we already derived, at least seen before. So from the statistical approach, we now derive the Sackur-Tetrode equation. Okay, and the final slide. Let's consider microcanonical versus canonical ensemble. Our description of the microcanonical and canonical ensembles was based on counting the number of accessible microstates. So what we had in the microcanonical ensemble. In the microcanonical ensemble, we fixed the total energy, volume, and number of particles in the system. Then we counted all accessible microstates and their multiplicity corresponding to a particular microstate. So the total energy U is fixed, but the temperature in the system is calculated using the averages. And so temperature can fluctuate in the microcanonical ensemble in the L-dilated system. Of course, it's very sharply peaked when n goes to infinity, but in principle the energy is fixed, but temperature is allowed to fluctuate. The probability of finding a system in one of the accessible states is just 1 over omega, or where omega is a multiplicity. So all states are equally probable. And finally, in the microcanonical ensemble, the entropy reaches its maximum, being a logarithm of the multiplicity. In the canonical ensemble, for a system in thermal equilibrium with a reservoir, the partition function now provides the number of accessible microstates. And we have temperature, volume, and number of particles fixed. Temperature is fixed, but now the energy of the system may fluctuate about the average value, and the average value we calculated before. So T is now fixed, but U can fluctuate. When n goes to infinity, these fluctuations suppressed by the size of the system, and so these two descriptions become equivalent because U and T both kind of fixed. The probability of finding a system in one of the states with the energy En is given by the Boltzmann formula, exponential Boltzmann factor over the partition function of the system. And the free energy is equal minus kT log of z compared to this formula. There is a next minus here. So entropy reaches its maximum, but here the free energy, here Horn's free energy, reaches its minimum. And the partition function, which is the analog of the multiplicity here, reaches its maximum. Okay. So this is all we need to know about the canonical ensemble. So I stop here and we continue next time.